Hi everyone, welcome back to 3 Deviations. In today's video, I'd like to talk about some examples with surface area. So in the last video, we talked about a lot of formalism of how we got to the formula for surface area, which said that if I want to find the surface area, we'll call that A, I can take the integral over a domain of the x partial derivative squared plus the y partial derivative squared plus 1 d squared x. And that would give me the surface area. Now we're going to try some examples, and we're really going to see the application of this, because it's like finding the surface areas of all of the kind of prisms and stuff you've been talking about in middle school, but we're actually bringing some more generalization to it, so because we're not dealing with those kind of shapes, we're dealing with shapes parameterized by algebraic functions. Let's try example 1. So find the surface area of x squared plus 2y in the region bounded by 0, 0, 1, 0, and 1, 1. So what does that actually look like? What does that look like? If I draw out my coordinate plane, here we have 0, 0, which is the origin, 1, 0, which is here, and then 1, 1, which is here. So we've got some sort of triangular region. We call that D. So D, we can write that as the ordered pairs x and y, such that x is between 0 and 1, and then y is between 0 and x. So now we want to use our formula for the surface area. What we want to find first is we want to make this integral, this integrand easy to deal with. So we're going to find what that is first. So if I find the square root of partial x squared plus partial y squared plus 1, well, if I take this function here and I take its partial derivative with respect to x, I get 4x, I get 2x, and then I get 2 for the y-th derivative, so we get 4x squared plus 4 plus 1. This leaves us with the integral between 0 and 1, then the integral between 0 and x of the square root of 4x squared plus 5 dy dx. Now, if I do that integral and perform the fundamental theorem of calculus, I get an integral between 0 and 1 of x times the square root of 4x squared plus 5 dx. Simple use substitution will take care of that, giving us 1/12 times 27 minus 5 rad 5. Okay, so that's one example that we can have. We also have the other example, which might be used in polar coordinates. So let's find the area of the paraboloid x squared plus y squared under z equals 9. So what does this look like? So a paraboloid x squared plus y squared, say general paraboloid, which is nice for us. So if I draw this out in the 3D space, it's going to be like this. It's going to be like this here. It's going to be like this, and then it's at the origin. So, well, actually, yeah, its bottom is at the origin. So if I draw this like that, there's our paraboloid, there's our origin, right? And when I say z equals 9, what I'm taking is I'm taking a surface and I'm cross-cutting it, cross-cutting this surface. So I want to find this area under here. Now, if I take this and I map this to the xy plane, I'm going to get a circle. Our cross-section is going to be a circle. So if I set both of these equal to each other, x squared plus y squared equals 9, then we get a circle. Our circle can be parameterized by polar coordinates, so I can get r equals 3, and that integral will be easier in polar coordinates. So now my domain is defined by r and theta such that theta is between 0 and 2 pi, and r is between 0 and 3. Okay, so now, again, we want to find our surface area, so we want to find our little square root thing. So if I find the square root thing in terms of x and y, I get 1, the square root of 1 plus 4x squared plus 4y squared. Obviously, we want this in terms of r's and thetas. We only really need to worry about r's because we can recognize x squared plus y squared as r squared, so we get the square root of 1 plus 4r squared. This leaves us with the integral between 0 and 2 pi of the integral between 0 and 3 of the square root of 1 plus 4r squared r d theta. Okay? Now this integral is fairly easy to do, so I'm going to forego actually writing it out because we're running out of room here. And if we perform the integral, what we get is pi over 6 times 37 rad 37 minus 1. All right, so that is surface area for you. It's really not too tricky of a concept once you get a couple of examples going through. In the next video, I would like to introduce the idea of a triple integral. So we're going to be spending the rest of the unit talking about triple integrals. I know this is a long unit, but that's the way it works in multivariable. Thanks for watching. We'll see you in the next one.